Hello, Al. Can you hear me well? Yep, good. Okay, so almost done with this class. It's a bit sad. I really liked teaching it. Hope you had fun. Um, so today we should almost be done with, or maybe be done with all the material. So yeah, the funny thing is, I think I told you last week, but anyways, I can explain it again. It's since you had the TD just after the class. Yeah, no, sadly, I'm not teaching the next one. Yeah, I wish I was. Yeah. But yeah, I'm sure the next teacher is nice too. And the yeah, it's the same book, and it's just a terrific book. So I think it's going to be nice. And in a sense, I could have continued a bit on the material and look at optimization with many variables and stuff, but I would have taken away from what he's going to teach you next. So, or he or she, I'm not sure. So, yeah, so okay. Yeah. So, one thing I realized, yeah, so let me finish what I wanted to say is that since we always had the TD just after the class, I sort of needed to be 1 week ahead of the material so as to give you at least a few days or 1 week to actually do the TD and yeah, the TA sessions and then be able to learn the material. So it means that I had to go fast. So for those of you who thought it was going fast, and I thought it was going very fast too, but that was a way of the schedule, and I tried to change it with the administration, and they wouldn't let me. So the result is that basically we're done 1 week ahead of time. So what I'm going to do is, so yeah, if I finish all the material today, next week there is a few things that I had planned on doing if I had too much time that I will explain a bit. And especially I would like you this week or next week to email me if some of the things we've seen made so give you more difficulty. So since we have time during the class, then it's perfect. We can go over it and make sure that you understand. And if you personally had trouble with it, then be sure that other students probably had trouble with it too. So it's going to be useful for everybody. So it's a sort of Q&A session for the last maybe half class. Or if I have too many questions, then I'm just going to not do the small material I wanted to do and just answer questions. So as to make sure that you're perfectly ready for the final exam. All right. So do you have questions before we start? Yes, Azim.
Yes. Do you have any other information on the final exam?
I have all the information I can have. So no, but I mean, it's the set is full. So I give you the time. The format is going to be the same, but exactly the same, but a bit but shorter in terms of time. So you have to be quick. And it's going to cover all the material, but obviously since I've already covered a lot in the midterm, then it's just saying, please do not forget the first half of the class. It's useful. So it's an incentive for you to just check whether you remember things well, and in case you forgot something or something was not as well understood, make sure you understand it. Yeah, but I have to test you more since it's a shorter exam and we have the second half of the class. So I'm going to test you more on that second part. I have no clue how many questions. I haven't written it yet. So it depends. Maybe it's 3 long questions or 10 short ones. Who knows? So, yeah. No, I'm not there yet. Yeah.
Okay, thank you.
My pleasure. Okay, so without further ado, let's get back to optimization. So let me quickly share my screen. Yeah. So we were discussing higher order derivatives. And this week, I read a bit more about the history of mathematics and notations, and I realized that I made a mistake previously, so sorry. It's not a material mistake, but it's a mistake about notation. So I told you that Leibniz notation for a derivative was something like this. So dy dx, this is for the first derivative. And then we're going to talk much more today about the second derivative, which is the derivative of dy dx with respect to x again. So if I derive it twice, then second derivative. So I would get the following. So this is sort of a function of x. And then if I take the second derivative, I get d this, d dy dx, right? So it's this y is an object. Then if I derive it, it's dy dx. So dy dx is an object. If I derive it, it's dy dx. But then what you see is d is just a operator that you can go around and mess with it, and it's like if you can multiply it. So you have dx at the denominator there and dx at the denominator there. So what you get is dx squared. And here you just keep the d at the numerator. So we write it this way, d squared y dx squared. So that's the second derivative. And then I told you that Newton notation was this, but it was a lie. So Newton's notation is like this. And so it's especially used when you take derivative with respect of to time, because Isaac Newton was interested in math as much as, or so he was even more interested in physics and mechanics per se. So he wanted to understand how planets moved around and objects moved and when you applied forces and everything like this. So all these derivatives were with respect to time. So even today, if you take derivatives with respect to time, then you usually write, well, you can write them this way. So instead of writing something like dy dt, you would write f dot of x if y equals f of x, for instance, and f double dot for the second derivative. So this is used in physics. And then the other notation that I introduced you is a notation by Lagrange, one of the great French mathematicians. And here, his notation is f prime of x, f double prime of x for the second derivative. And what's very neat about Lagrange notation is that you can generalize it to, so if you have, say, f prime, 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 so you can just write f, so fifth derivatives, for instance. Fifth derivative. So you can write f1, 2, 3, 4, 5 of x, but you can simply write it more concisely like this, f5. But what's very neat is that there is, so the fundamental of theorem of calculus is that the antiderivative or the integral is the opposite of the derivative. So integrating a function, it means to add up the area under the function, and it's exactly the same as if you the reverse as starting with the integrated function and take it in its derivative. You're going to learn that later, or maybe you already know a bit. And what's neat is that you can use Lagrange notation as well for that. Simply, if you want to integrate f once, you take f minus 1 of x, it's the integral of x, and then f minus 2 of x integral a second time. So you can generalize this notation. Yeah, and f minus 5 is taking 5 times the integral, but I doubt anybody in the history of mathematics has ever taken 5 integrals. Or maybe they did, but yeah, usually it's you don't write it this way. Usually the common notation for integrals, yeah, if you have say f of x is integral from x0 to x1 of f of x, or f, no, not of x, but f of some, let's just say f of z. This. We don't like to put x here because this is something that's going to run from x0 to x1. But yeah, that's later. Do not worry about it. Okay. Sounds like there would be more unknown. Yeah, that's the problem. Is you need integration. You need a lot of you need either boundaries or you need to add a constant of integration. So if you have -2, -3, I don't know what's going on. It's just I read that you can write it this way, but then don't ask me further. Yeah. So for those who don't know, integral has to be between 2 points. Derivative can be is just the slope of a function at a precise point, but integral has to be taken between 2 points. And if you don't do that, then you need to add some constant of integration. But yeah, don't worry about this. Okay, so let's go ahead and define another concept, smoothness. So let me just see what smoothness is. A smooth function is continuous, but it's a sort of generalization of the concept of continuity to higher order, to derivatives and higher order derivatives. So that's the first condition. So if it's not continuous, it's not smooth, you cannot do anything with it. And just a reminder, a continuous function is some function that you can write with a pencil without lifting the pencil. And then what is smoothness? So smoothness refers to the number of derivative which can be taken over the whole domain of the function. So once we look at examples, it's going to be very clear what we're talking about. This is just, sometimes you're going to hear this smooth function or smoothness, and it sort of makes intuitive sense. Yeah, probably it has to not be too, not have too many kinks in it and breaks in it. But so what does that mean? It has a exact mathematical definition, and this is it. So so example. So y equals absolute value of x is continuous. But it's not differentiable. At x is equals to 0. So since I include 0 in the domain, then I say that f of absolute value of x, oops, why did I write this? I wanted to write y equals absolute value of x. So it is not smooth. So there's a kink. So absolute value is just like this. So if there's a kink at 0, then it's not smooth because you cannot take the derivative at 0. Because if you look on the left side, is going to give you a negative slope, and on the right side is going to give you a positive slope. So there's a break. So we note it C0. So C because it's continuous, but 0 because you cannot take a single derivative of this function, at least at 0. Then a polynomial function. Let's take an example. So f of x equals to 3x squared plus 34x plus 3. So is that continuous for any x? Yes, is continuous. And is it smooth? Yes. So how many times can I take, how many derivatives can I take from this function? If I derive 3 times, what do I get? I get 0, but I get 0 everywhere. So it's continuous. It's still continuous. So I can derive it as many times as I like. So, and it can be derived and exactly infinite number of times. So it is infinitely smooth. We write it C infinity. And now a more challenging one. So it's just because so I get f prime of x equals to 6x plus 34 if prime of x equals 6, then if I derive 6, I get 0. And then if for x is 0, and I can go on and on and on. So it's as long as the curve is always smooth, I'm using as the curve is always continuous, then it's perfect. Now, the only way I found that I could define a function that's either that is not either C0 or infinitely smooth is by defining it by function, by section. So let's go ahead and do that. All right. So y equals x squared or 0, and f squared is going to be for x smaller than 0, and 0 is going to be for x greater or is equal to 0. So is this continuous? Yeah, I think, Patrick, you're exactly right. E to the x is infinitely smooth because it's you always get the same thing. So yeah. Yes, as in you're perfectly right. Why? Because so obviously, anytime I ask you a question, is something differentiable or smooth, then so what could possibly go wrong? Well, either you divide by 0 somewhere, so you get a mess, or if there's no division, it's not that you get some singularity. But what I can give you is something that's derived in parts. By sections, and then obviously the problematic point is the 0 there. So you have to check at 0. So yes, because 0 squared equals 0, so it's continuous. And is it smooth? Yes, but which degree or order do we say order smoothness or degree of smooth? I'm not sure. Anyways, it's see how many. Is it infinity?
But Professor, if we write C0 and C infinity, then it's always either or, right?
Yeah, exactly. But my question
Okay.
is, so you could have something in between. So
Oh.
here I'm sort of defining something in between. So let's go ahead and, okay, let's derive it. So dy dx is going to be equal to 2x if x is smaller than 0, and it's going to be equal to 0 if x is greater or equal to 0. So then is the derivative the same at 0? So it means that, yes, you can derive it everywhere. So it's at least smooth of order 1 or degree 1. But then let's take its second derivative. So d squared y dx squared. What do I get here? This is 2. And here it's still 0. So there's a discontinuity at 0. So if I were to check to write it really to use the definition of what is a derivative, then you would see that the left derivative and the right derivative are not the same. So you cannot derive it. So at x equals 0, the derivative is discontinuous. Or you would just say does not exist. So then we conclude that it is C of order 1. Yes, Izzy?
Sir, I didn't understand. Derivative is the same at 0. Why are we saying that?
Oh, because if you take at 0, so you dy dx equals 2 times 0 equals 0. If
Oh, okay, okay. Okay, got it.
And let me show you graphically what this function looks like. All right, so this is y squared, and this is 0. So this is this function there, y squared and 0. And if I take the first derivative, then it's f prime of x is 2x. So it's on the negative side, it's in the negative there. And then it becomes 0 at for positive values of x. So you see that the derivative is a continuous function, because at 0, I don't have to lift my pencil to draw it. But there's something that goes wrong here. There's a sort of kink. And what does that mean for higher order derivative? If I take the higher order derivative, f prime of x, then here it's 2 plus 2 plus 2 plus 2. And then here it's 0, 0. So there's a discontinuity there. So this is going to why we say that this is C1. And f prime of x would be C0, because you cannot take the derivative. This would be like absolute value. It's the same problem. All right, does that make sense? So this is just to to define terms when I talk about smooth functions. So I'm saying that you can at least take a first derivative everywhere, but it can be, you can have a higher order smoothness. Yes, Patrick?
Yeah, I was thinking it to be C2 because even when we graph f prime of x, it's still connected at x equals 0. And we could still take the derivative. And then I get that at f double prime of x, it's
okay, so
discontinuous. So why,
yeah, so
why
it's
would
just a
that
matter.
logic make it C1?
Yeah, it's just a matter of definition. So we conclude that f of x is C1 because the derivative is a continuous function, and f prime of x is C0 because it is continuous, as you rightly say, it's continuous, but its derivative is not continuous. And
right, because of the kink.
yeah,
the
exactly.
kink in
And
the
f prime
graph.
prime of x is simply not continuous.
Okay. Thanks.
Yeah, but so for normal function, either they are this way or they are polynomial functions like this that are infinitely smooth. So that's why we usually people are going to say it's smooth, and then you don't really have to worry too much. Is it smooth of like C1, C2, or C3, or normally when something is smooth, it's really well behaved. But just to make just to add to your vocabulary, so that's what we mean. Okay, so back to optimization. So what can we interpreting of the second derivative? So if I have a second derivative, so of f of x. So if the second derivative f prime prime of x is greater than 0, it means that means two things. So I can, for instance, go to here. So here what I see is f prime of x is increasing, but steadily. So the second derivative is, yeah, okay, it's not a great example, but yeah, I would have to go back to, let me see if I have previous examples. Yeah, okay. Use my previous example. Okay. If f prime prime of x is greater than 0, so the second derivative is positive. So it means I'm in this situation there. It means that the slope, the first derivative, tends to increase. So you see that it's negative here, then it's 0, then it's positive. So I'm in this situation there. So it means that the slope of the curve tends to increase, And the slope is, of course, f prime of x. And we also say that f is strictly convex. And then I haven't defined what is convex. Maybe some of you know, but I'm going to give you a more precise definition later on. So when we define convexity and or concavity, it's always with respect to the, so yeah, it can either be a when we describe a set of number or a function. If it's a set of number, then we say that any linear combination of two elements of the set is in the set. This is what it means to be convex. For a function f like this, one variable function, then we define convexity with respect to the the origin, so the zero value of the y-axis. And what we say is that if I take any combination of two elements of any linear combination of two elements of 2 points of the function, then they are always above the function. And if it's concave, then it means that if I take, say, this point here and this point here, and I draw a straight line in between, then and I take some point on the straight line, then it's going to be below the function itself. So this is what it's going to be mean to be concave. But yeah, I'm going to talk a bit more about it later, so do not worry. It's just that there are always a lot of terms to define. So, so know that this link between the second derivative and convexity and concavity is very useful, because it's often much easier to just take the derivative. When I ask you, for instance, is something convex or concave at some point, then it's, if you just can take the second derivative, it's just super easy to do it. Whereas if you use the definition I'm going to use later, which is a proper definition, but still not very wieldy, not very easy to use, then it's less easy. Okay, so let me just go ahead and state the opposite case. Oops. So if the second derivative is negative, it means that the slope f prime of x of the curve tends to decrease, and that f is strictly concave. So we are in this situation there. If the second derivative is negative, then it means that the first derivative or the slope is decreasing. So here it's positive, 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 but less and less and less steep, and then it's zero, and then it becomes negative, negative, negative. So it means that the second derivative, so the derivative of the derivative is negative. And it also means that around, say, this point, then the function is going to be concave, not convex. Does that make sense? And this is what we use to know if we are dealing with a minimum, which is this point, for instance, and a maximum, which is this point there. Okay, so let me just derive concavity really quick. This is this accepted definition for concavity, but using the sign of the second derivative is much easier oftentimes. So let me for some number t, let's just use t between 0 and 1, and some value x that are different, that is different than y, then we see that a function f is strictly concave if f of, and then if I take a sort of midpoint between x and y, so I take tx plus 1 minus ty. So it could be like if t is 0.5, then it means that I take the midpoint, midway point between x and y, so 0.5x plus 0.5y is strictly larger than t times, so f of x plus 1 minus t times f of y. And this is what it looks like. Okay. So if I have x and y and t is some point in between. So if I take f of tx plus 1 minus ty, which would be f of tx plus 1 minus ty would be here, then this is greater than the average of f of x and f of y, which would be tf of x plus 1 minus tf of y. So this is what we mean when we say concave. And the opposite for convex. So if a function, a function f is strictly convex, and the opposite is true, of course. If this is below this, so f of tx plus 1 minus ty is smaller than tf of x plus 1 minus tf of y. So again, what we're saying is t is used to take a sort of weighted average of both values. And oh, I didn't draw it. I don't have a drawing for that. So the drawing looks like this. Like this. So let me take take that again. Looks like that. Yeah, it's not super professional. I thought I had a graph for both of them, but yeah, you get the point. So this is the definition. But so what's neat is that there's a strict correspondence between this definition applying and the second derivative being negative. And here, sorry, this definition there. And if this definition applies, then the second derivative is positive. So that's very helpful. If you want to check whether something is convex or concave, then either you check this, but it can be tedious to do, or you just check the sign of the second derivative, and that's easy. All right. So now we can really finish our definitions of minima and maxima. So, oh yeah, and by the way, let's leave this way. So then, for minimum and maximum. So this is our complete definition. So a point C represents a relative minimum if f prime of x1. Well, yeah, the point C, but so there's x1 there. F prime of x1 is equal to 0, and f prime of x oh no, what? I'm sorry. I'm rewriting stuff that I already wrote. Yeah, okay, so scratch that. For smooth curves, so if curves are not smooth, then a minimum can occur at a kink, of course. But if the curve is smooth, then a necessary condition for a local optimum is that the first derivative, f prime of x, is 0. So we already seen this. And we are going to see that a sufficient condition for a maximum. So necessary means that if the curve is smooth, it must be the case that f prime of x equals 0, but it's not enough to be sure that it's a maximum or a minimum. So to be sure that it's a maximum, this must be true, and you add the second condition, which is this one. Second sufficient condition for a maximum is that f prime of x is positive or negative for a maximum. I forgot. Yeah, negative. So it's this case. So this is a maximum because the derivative is 0 and the second derivative is negative. And of course, a sufficient condition for a minimum is that the second derivative be positive. All right. So that's it. That's optimization for a single variable function. So I went through a lot of pain to say what convex concave is, what a smooth function is, just to make sure that we have the same terms. And now for the future, if you hear smooth curve, you know what we're talking about. So if the curve is not smooth, then you could have a minimum or a maximum or anything at kinks. So the function could look like this, and you have a minimum there. But if it's smooth, then this is what's going on. So necessary condition is the first derivative is equal to 0. And sufficient for a maximum is that the second derivative is negative. Sufficient for a minimum is that the second derivative is positive. So back to our previous example. So let's take f of x equals x3 minus 12x squared plus 36x plus 8. So if I want to find the extrema, what I must do is take the, so first of all, this is a smooth function. This is a smooth function. So to find the we take the radius. So f prime of x equals to 3x squared is 24x plus 36. And we say that the so first order condition or we write this FOC, first order condition, or the FOC is that f prime of x equals 0. So let's do that. We want so using the quadratic formula, x equals minus b, so it's 24 plus or minus square root of 24 squared minus 4 times 3 times 3, 6 divided by 2 times 3. So x will be equal to my guess is that I used the nice numbers. Yes, so this gives me 144. I have to teach this class live next year, and I'm going to miss this. Yeah. So it's equal to plus or minus 12. So let's divide by 6. So I get 2 here and 4 here. So that's either 6 or 2 or 6. Yeah, that's what I was getting. So now I have 2 zeros of this first derivative. So it means that these points are the points of interest, the places where stuff happens in my function. I might get minimum, maximum, or inflection points too at this point. So who knows, to make sure I have one or the other, I have to take the second order condition. So to know whether my critical values are either maximum or inflection point. I take the second derivative at these points. So let's go ahead and do that. So yeah, this is the second, by the way, the second conditions. So second derivative is f prime of x equals 6x minus 24. And then I don't set this to 0. What I do is I check for every x that interests me, whether this is positive or negative. So verifying. X equal 2. So that's my first candidate. So see that second derivative at 2 is 6 times 2 minus 24. So this is close to minus 12. So it's smaller than 0. So 2 is a what? Maximum, yes, great. Then I can verify that at x equals 6. So what is our guess for 6? So I mean, yes, think about this shape there. If it's a third order equation, then third order equations look like this or like this. So they have so the curvature. So if at one point there's a maximum, then your best guess is that at the second point it's probably a minimum. Or if at one point is a minimum, then your best guess is that the next one is probably a maximum. So we're going to, so if it would be extremely, extremely weird if you had only 2 candidate solutions and both were a minima. So I don't think that would, I think that would break mathematics. All right, can you go over how to navigate this step? So if I explain again what I did, so tell me when you're when it stops making sense. So I have some function. Yeah,
I guess it's just because in our last class you said step 2, look at second derivative to confirm. So I don't get where like the second derivative, if it's positive, it's a maxima, if it's negative, it's a minima, and if it's 0, it's an inflection point.
Okay, so
Like,
so yes,
that's where I'm confused.
Let's look at this. So C, you agree with me, this is a minimum, right?
Yes.
So what's going on at C? Well, if I look at the first derivative of f, then it's negative, negative, negative because it's going down. Here it's 0, and then it's going up. So the first condition, the first order condition to get a minimum is that the first derivative be 0 at this point. So what I did, I took the first derivative and look at all the point at which f prime of x is 0. And here I found 2 points. I found 2 and 6. But so here I don't have a specific value, but here I see that it's 0 at C and at D. But so just the first derivative being 0 is not enough. Why? Because you can look at D here, and the first derivative is 0, 2. But D is not a minimum, it's a maximum. And how do you differentiate whether it's a minimum or a maximum or an inflection point? So you look at the value of the second derivative. So here the second derivative is positive because the slope is starting from being negative and then 0 and then positive. So it's always increasing. And here it's a maximum because the slope starts positive and then 0 and then negative. So it's always decreasing. So at point D, it's
It would be negative second derivative.
yeah, exactly. So you look at the
So-
second derivative to differentiate whether it's a minimum or a maximum.
Yeah, so at the minimum, our second derivative is positive, and then at the maximum, it's negative.
Yeah,
And
Uh,
if it's 0, it's an inflection.
yes, exactly. So yeah, and so I should add that. So if the second derivative is 0, it is an inflection point. So we are going to see this just after that. So yeah, we check at x equals 6, and we see that f prime of 6 equals to 6 times 6 minus 24. So that's 36 minus 24. So that's oh, I can't compute today. 12. So it's positive. So indeed, we have a minimum at x equal maximum. Sorry. No, sorry, a minimum at x equals 6. Yeah. And then example of an inflection point. So let's use y equals x cubed. So first derivative so dy x equals 3x squared. Yeah, so first order condition. And then so we set this to equal to 0. So we get that x is equal to 0. So we know that something fun isn't happening at 0, but we don't know whether it's a minimum or maximum or inflection point. Second order condition. So d squared x squared is equal to 6x. So at x equals 0, we see that is equal to 6 times 0 equals 0. So we know that indeed, so neither a minimum nor a maximum but an inflection point. An inflection point is exactly a point at which the rate of change of the derivative switches. So was negative and becomes positive, or was positive and becomes negative. Yeah, so let me draw all these curves there. So graphically, so what is it? It's I want to draw this curve there. Oh yes, so let me take a better. All right, it's a bit too large. So we have our two critical values at 2 and at 6, as we've seen. And the second derivative at 2 is negative, so we know we have a maximum. And the second derivative at 6 is positive, so we have a minimum there. And as we know, if it's a third order, then probably it looks like this. So if we have one that's maximum, then you can bet your life that the second one is a minimum. You cannot have two maxima without a minimum. It doesn't make any sense geometrically. So since if you find that, for instance, 2 is a minimum and 6 is a minimum as well, then check your calculation. You probably have made a mistake somewhere. And then the second case, so let's just draw it quickly. We know what it looks like, but just for fun. Sorry. All right. So we have a critical value here, but it turns out that it's neither a minimum nor a maximum. It's just a place at which the derivative was decreasing, and just when it reaches 0, then it starts increasing again. So it's just a very special point in which nothing is really happening. But if you're not careful and you just look at the first derivative, you think, oh yeah, I have some minimum or maximum there, but no, it's just an inflection point. All right, so does that make sense?
Yeah, that makes a lot of sense.
All right, so let me now check whether it really makes sense or not. So let's have a small quiz. There. Oh, I'll put that in the chat. Yeah. Sorry, I'm going to have a message for everybody. There. So use your pencil and pen or computer. And yeah, the last quiz I gave you was very, very hard, I realize. Way too hard. So this one, hopefully it's not too difficult. But still it can, yeah, it's an interesting quiz. To check whether you remember your derivative rules and stuff like that. Oh, and I realized that the first question is exactly what I just talked about. Okay, I forgot, I'd forgotten about this. Okay, so I hope the first question and the second one, you do well.
For some of the questions, like the answer, like for critical values, there's two answers, but you can only select one option.
Oh yeah, are you sure? Okay, let me check that.
Yeah.
So
Like for question 3.
question 3. Yeah, you can only select one. Multiple choice. Oh. Oh, so maybe I should have used checkbox. No, it seems like, okay, I understand what's going on. All right, so checkbox it is. So can you try now or maybe reload the thing? Reload the quiz, maybe it's going to work now.
Yeah, it works now. Thank you.
All right. Yeah, I realized, so what it is I can select many right answers, but then I thought, okay, so if I can select many right answers, it means you can, but no, apparently not. So yeah, the checkbox, it works. Oh, and for the, yeah, I'm going to, yeah, and for the other ones too, I have to use checkboxes. Checkbox. Checkbox. Okay, so now this should all be checkbox. Anyway, so of course it doesn't count for anything. The trick, you could just do it on your own. It's fun to have to see what people answered. And now I'm going to check the next quiz I wrote to make sure that it's okay to. Oh yeah, so the other one, it's multiple choice books. Well, actually, what we can do, since it's already 10, is take a break now, and you can take your time and finish it. And we can then come back in 12 minutes. So that's my time is 10:05. So let's come back at 10, 16, 17, 18, something like this. And we are back. And we have lots of nice answers. So let's go ahead and correct this. All right. So first question is find the critical value of f of x equals x squared. So yeah, most people remember that the critical value is at 0. How do you do that? You take the first derivative. And then what is this critical value? Everybody got it. It's an inflection point. Why? Because the second derivative at 0 is 0. Now, this one is a bit more tricky, but still most people got it right. Find the critical value of the function f of x equals 1 over 1 plus x squared. So yeah, if you want, later on, I can show you how to derive it if you didn't remember. So yes, the critical value is at 0. And what is it? It's a maximum. Most people got it. Some thought it was a minimum or an inflection point. Then again, we can discuss this. Third one was a bit tricky too. What is the critical value of x squared minus 12x? So it's going cube. Sorry. So x cube we already know. It looks like this. So minus 12x. So minus 12x looks like this. So you can more or less guess that it's going to create some kind of curve in the curve, where we are going to get a minimum there, a maximum there, and a minimum there. And yeah, the two critical values happen at -2 and +2. And yeah, so this, I think it's because I messed up with the quiz, but we get one minimum and one maximum. Yeah, so we get both. All right, so not bad, not bad. Yeah, so let's just look at the of x equals 1 over 1 plus x squared. So every time I get this, I think it's easy just to imagine that I have that this is 1 plus x squared exponent -1. So then you just deal with it as you would any positive exponent. So so you can write it this way. So f of x equals 1 plus x squared to the -1. So we get that first derivative is f prime of x equals -1 plus x squared to the -2, multiplied by the derivative of what's inside using the chain rule. So it's 1, there's nothing going on there, it's 0. So you get, in this x squared, it's 2x, so times 2x. And then the third derivative is double prime of x, which is equal to here, this is, I have some x here and some x here, so I'm going to get, it's a product. So it's the derivative of this one times 2x plus the derivative of 2x times this part there. So I get this. So the derivative of this section there is -2 in front. So I get minus, so I get 2. here I get -3 plus then this times the derivative of 2x, which is just 2. So you see that what I did, it's always it's a product of two functions. So the derivative of the first one times the second function plus the derivative of the second function times the first function. So here I split them. So first order condition is that f prime equals 0. So this must equal to 0. And well, this is always positive, no matter the value of x. So I don't have to worry about this. And then 2x is 0 when x is 0. So I find that x must be equal to 0. And then the second order condition. So let's see when x is 0, what is the sign of this? So second derivative of f at 0 is equal to this. So I get 0 here, 0 here, 0 here, and that's it. So what do I see? I see that this is 1 plus 0, it's a 1, but here I get 2 times 0, so this disappears. And 1 plus 0 squared is 1. So 1 to the -2 is 1, so I get -2. So it's smaller than 0, so it is maximum, as most of you got it. Yeah, so it's a bit tedious because you have to be sure you don't make a mistake in computing the derivatives, but yeah, other than that, it's straightforward. And let me just show you what this function looks like. Sorry for taking long. Sometimes my print screen function doesn't work properly. All right. So it looks like this. So indeed, at x equals 0, the first derivative is 0, and the second derivative is negative. So I get a maximum. Question. Does this function have, and here I'm not expecting you to know the answer, but just tell me what you intuitively think. Yeah, so yeah, you're very smart. So it's exactly. So it's looks like you have a minimum, but it sort of doesn't look like it. Why? Because you have a minimum at the either at the limit of when x tends to infinity or minus infinity. So not really, because yeah, so because yeah, you couldn't say that. So whatever x, because you can always find an x for which f of x is smaller than some other. So we have another concept. So the is infimum. So it's what it means is the largest value that is smaller than all possible values of f of x. Yeah, although k over x, you would have, it would be k over x can go as little as possible. So here it's really so you wouldn't even say that it has an infimum. But so this really, that's just for your personal mathematical culture. You don't have to know about it. But yeah, so that's if you get something that looks like this, it looks like asymptotically, it never reaches something that's smaller than 0, but never reaches 0. So it's called an infimum. So it's the largest value that is smaller than all the possible values of f of x. But don't worry about this. All right. So for the rest of the class, I want to show you one or two small examples, then show you Taylor's theorem, and then maybe come back with a slightly more involved example, just so that you get the Taylor theorem and you can do all the questions in the TA session, because there is one question about the Taylor theorem, and it's a very neat theorem. So, but yeah, we're almost done. So some applications of optimization in economics. All right, so yeah, so for the second one, the third question, check on your own. So if you have time, you'll see that yeah, you understand what's going on. All right, so you may remember that the firm revenue is maximized when elasticity of demand is unary. I think it's how you write it, or unity is -1. So do you remember that a bit or not? Does that ring a bell to anybody? Kinda. All right. So, well, we have time. So yeah, long ago. So let me show you what. So yeah. Okay. So this Isaac. So I'm sorry for you because that's what I've seen too, is how do they teach economics at Concordia. They show you how to compute elasticity, and then they tell you that for whatever reason demand elasticity is positive, but demand elasticity is never positive. But I mean, so I've been teaching microeconomics now, and I've been clashing with all the other teachers. So it just makes my hair explode when I because elasticity. So yeah, let's just a small reminder. So inverse demand is, yeah, I know that they're annoying, but yeah, but so it's because we show students how to compute elasticities with a formula, and then at the end of the day, whoops, the minus sign goes away. So it's just you can just say we take the absolute value of the elasticity, and that's exactly that's fine. So in that case, yes. So or let me see, or the absolute value of demand. So inverse demand is P of Y. So it's how the price changes when the monopoly increases the production. Revenue monopoly is production times P of Y, or P of Y times Y. So you would say, you would write it as R of Y. So it's how much revenue I get when I produce a certain quantity, knowing that what is this revenue made of? It's made of the total amount of stuff I produce multiplied by the price I'm going to be able to sell in the market. But since I cannot sell at multiple prices, it's not a monopolist that can discriminate, then all these units are multiplied by the same price. And this price is itself influenced by the quantity on the market, because I have to be mindful of how much people are willing to buy. And the more I want them to buy, then the lower I get. I can sell them. So it is negative. So P prime of Y is smaller than 0. So the first derivative of the price with respect to Y is smaller than 0. All right. And then elasticity. So the elasticity is, so you write it epsilon of, yeah, just epsilon of something. It's equal to dy dp times p over y. So dy dp is how much people are going to change their consumption when the market price changes. And then to get something that's in terms of proportion, so it's, yeah, it would be something like Py divided by y, p. And what you can do is just pull out the y and the p. P goes at the numerator and y goes at the denominator. So this is what you get. And note something. So here I start with p of y, but here I need a demand, not the inverse demand. So the demand is y of p. So we already have introduced the concept of inverse functions in economics because sometimes we had inverse demand. Well, most of the time on the graph we see inverse demands. And then sometimes we need the demand, which is the inverse function. Okay. And then, so imagine I want to maximize the revenue. So what should I do? Well, I check for a maximum as I would for any abstract function. All right, so the way you will write it in your long and fruitful career as economists is the following. So you write max of y. Yeah. So you say what you're looking for. So this is the definition of the problem you're going to solve. So max, and then underneath you say which variable you're going to use. So it's going to be a function of the quantity produced. So max by choosing the variable y. So you're choosing the variable y that's going to maximize what you're interested in. And here, what you're interested in is r of y. So this is how you write the problem. And yeah, so for the first order condition is going to be that you set the r of y, dy equals to 0, and you check for which value this is true. So for which value of y this is true. So I have y equals p of y. So I have p of y times y. So it's a product. So again, it's the derivative of the first times the second, plus the derivative of the second times the first. So it's equal to, so this is going to be p prime of y times y plus p of y times dy dy. So it's just p of y. And you get, so what is this effect there? Well, let's first start with this one. So what does that mean? It means that if I increase 1 unit of production, then I get the extra sales price for my revenue. So I'm happier, I make more revenue. But what does this term say is that for all of the values that the units I was already selling, then the sales price is going down. So I have to be mindful of these two countervailing effects. So this tends to increase my income, but this tends to decrease my income or my revenue. And then I set that to 0. So, and then I could check a second order condition, but I'm not going to, but because I don't know what the shape of p prime of y is exactly, but no, yeah, let's just check it for small bits. So I will get what I would get. T squared of y squared. And this is p double prime y plus p prime of y times y with respect to this one. And here derivative of this with respect to y is p prime. So it's equal to plus 2p prime of y. And this must be negative. So is it? Well, I know that p prime of y is negative, but here I don't really have a specific value for p prime prime. So what you have to assume is that this is small enough. So we must assume this is smaller than, or yeah, must assume that this is smaller than 0. So that so to be sure, so p double prime y must be smaller than 2p prime of y divided by y. So, but usually we use a simple linear function for p of y. So this is equal to 0. But so if I don't give you any specific function, then you're not really entitled to say that the second order condition is respected. But since I'm taking a maximum, I assume this is the case. So this is really a side note. That's why I wanted to put dot there and not care about it. But yeah, let's do it properly. And this we have to be mindful of this. But if we're looking for a maximum. Yeah, so this should be smaller than 0. All right, so, but let's go back to the first order condition. So we have this. So what do I know? I know that this must be equal to minus p of y. Yeah. Or rather, let me switch these two. And then what I can do is simply divide by this on both sides. So minus here. Then here I get -1 divided by this. So let's have 1 over p of y here. And what is p prime of y? So note p prime of y is dp dy. So 1 over p prime of y is 1 over p o dy and using the inverse function rule. So as long as it's non-zero, then I can say that this is equal to dy over dp. Yeah, so then I get this. And this is, of course, the elasticity. All right, so that's how you get. So yeah, I took longer than I thought. It's just a simple. You just when you do this, you're almost done basically. So, but yeah, I put much more detail than I thought. Does that make sense? So here it just shows exactly that if you maximize the revenue by choosing Y, then you can instantly find that this implies that the elasticity of demand is equal to -1 at that point. Questions? Did it go too fast? Are you too confused to ask questions? Okay, well, if there's no comment, no question, I continue on. Second application. You may remember that the marginal cost crosses the average cost at its, do you remember that? Minimum, yes. And again, so now we have a minimum there, so we can use calculus. We can use what we know about derivatives to verify that this is the case. So consider a cost function C of y. So the average cost is, let's write it AC of y equals, so the average cost, it's for the average cost over the production, so it's C of y divided by y. All right, and now let's compute the minimum average cost. So, well, let's write it properly. So not max, sorry, min AC of y by choosing y. First order condition, d AC of y dy equals to, so I have, so let's write it dc here, dc dy y times y minus derivative of y is just minus, it's just 1, so minus, and then derivative of y multiplied by c of y, so cy. Then this is divided by y squared. And this must be equal to 0. All right, so here y is always positive, so I don't, well, unless it's 0, but then it's a degenerate case. So I'm interested in the positive values of y. So then what I deduce is simply this, that c of y minus y equals 0. So let's just divide by y. So I get that is equal to c of y, and I can just divide by y. And what is this dc of y? Where? Is what? Oh, oops, I did marginal cost, average cost. Well, I didn't write costs there. Yeah, so marginal cost function. So yeah, this is a marginal cost. Yeah, dy. So you may have seen. You may have. Delta c of y, delta c, delta y. It's the margin. So this is just the continuous version of it, so their derivative. So what do we see? We see that, so what do we get? Get that. This is the marginal cost of y. And this is the, what is this? Average cost, yes. So that's it. That's just, you just take the first derivative and you know that, okay, but yeah, to be sure, let's look at the second number. This. So, then the second order condition is d squared of ac dy squared equals to, yeah, again, I get this. Yeah, that's what I don't like with the abstract function, is then I have to say things about second derivative that I don't really know for sure. So this is usually why we don't check that it's, but yeah, you know, normally you should. So here we get this. Oh yeah, it's a real mess. All right, so plus, So this, that multiplies y squared. Oh yeah, no. Still I have to minus dy. All of this that multiplies y squared minus 2y, because that's the denominator that multiplies what I had at the numerator. And then this is to the fourth. So squared again. And this must be positive. So since we don't know dy, we can't be sure, but assuming this is 0, it's true for linear cost function, then we get so this is 0. So this is oh, this cancels out. That's neat. Is that the case? Did I make a mistake there or not? What was my numerator? Yeah, no, that works. So this cancels out. Okay, I didn't make a mistake. So this is 0. And then, yeah, this is okay. That's quite neat actually, because look at this there. dc of y dy, y minus c of y. But then the first order condition says that dc of y dy is equal to 0. So I get that this is equal to 0. So does that mean? Oh yeah. Okay, so that's not true at all what I was saying. Sorry, I was blowing smoke. Yeah, we know the shape of this because the cost function has to be increasing. Oh yeah. Okay, sorry, I hadn't thought to that point. Yeah, so that's we know that this has to be positive. Yes, because the cost. So what did I get there? All right. Yes. Okay. So let's go ahead and do again what we were doing. So this is 0. So we'll get this is 0. And this is 0. Okay. So I get this disappears, this disappears, this disappears. Okay, it gets very, very simple. 1 over y. And then this is positive because I said that this is positive. So we get indeed have a minimum. Okay, that was I didn't prepare at all this part, but yeah, I remember that this is a necessary condition. I hope I didn't lose people. So anyways, my point was this up to this point. But so anytime you do a optimization problem, then you should check the second order condition. Yes, Azine?
So then we don't assume anymore that the function equals to 0. So true for a linear cost function.
Yeah, no, it's stupid, because if it's a linear cost function, then it doesn't have a minimum. So it was really a stupid thing that I said. Yeah, because I was again thinking about the demand function, and the demand function we can have a linear function, and it's fine. But yeah, for a cost function, if I wanted to have a minimum, then it must be the case that the second derivative is positive. Otherwise, there is no minimum. So that's essentially a proof that that what I've been saying is true. In the sense that if the second derivative of the cost function is not increasing, then it cannot be minimized. Does that make sense for everybody?
Yeah.
Okay. So yeah, sorry about messing that up. Yeah, all of these examples, I just thought, oh yeah, first order condition, but then I thought, oh no, it's not nice of me to to not show the second order condition as well. Okay. Last theme for today. Taylor series. So let's see how far we get. 20 minutes. Yeah, we have time to do it, I think. So this is more advanced stuff. But it's very interesting. So what are Taylor series? They're a way of approximating any function using derivatives. So so this is very neat because if you manipulate, yeah, and getting an algebraic, no, polynomial expression. So why do we care about this? So this Taylor series, you're going to see this everywhere. In macroeconomics, in physics, in chemistry, anywhere, because the world is messy and you have to deal with messy functions. And sometimes you cannot do anything with them because they're complicated to deal with. And you would like a way to approximate them with a neat expression that's easy to compute right away. And if you have something that's 1 plus x squared, for instance, then this is very easy to deal with. But if you have something like log of x, or if you have sine of x or whatever, then this becomes extremely unwieldy and extremely difficult to deal with. So every time we would like to have an polynomial expression that describes the phenomenon we want to look at. So, and what Taylor shows. So Taylor series are derived from Maclaurin series, but we're already going to look at Taylor series. So, and we are going to look at them through an example. So let's take an example. Let's approximate log 2. What is log 2? Well, I have a computer and it's going to be equal to numerically 0.69315. So how do I know that if I cannot compute it? Well, Taylor's idea is to start from a point at which I know a lot about the function, and then look at how the function is changing from that point to the point that I want to estimate, and then use as much information as I can from the point I know about to get an idea of what the function should be where I don't know about it. So is there a point where I know a lot about the log function? Somebody remembers the log function? Is there a point around 2 where I know a lot about it? Oh, yeah. All right. Oh, I hadn't thought of that. ln of E. Yeah. All right. I could have at 1/2. No, ln of E is nice, but yeah. 1/2. What is log of 1/2? Do you know?
Oh, sorry, I was thinking of the derivatives. Never mind.
No,
But maybe,
yeah, that's
okay.
where we were going. That's where we're going.
Okay.
But so think about a point at which we know a lot about the log function. No, nobody? It's not 1/2?
Log of 0.
Yes, no, log of 0 is minus infinity. Okay, we know. Yes, good. Thanks, Azin. So log of 1. So what is log of 1? It's equal to 0. So that's the first approximation. I know that the log function looks like a weird curve there. So I know that log of 2 it can't be 10,000. It's bound to be close to log of 1 because it's a continuous function. So it's a good start. So 0 is a good approximation for log of 2. But can we do better? Well, turns out that log of 2 is 0.6. So 0.6 is higher than 0. So why do we have a bad approximation? Could we have guessed that that log of 2 is bigger than 0? All right, so let me show you the log function real quick. Okay, so log of 1 is 0, but log of 2 is not 0. And one way to anticipate that it's higher than 0 is that the slope at 1 is positive. So we know that the function is increasing. So if when we reach 2, it should be higher than its starting point. So a better approximation would be to look at this and say, okay, well, at 1, what is the slope? And then I can just anticipate, okay, it's going to go from 1 to 2, so 1 unit to the right. And during that time, it's going to increase more or less by the slope of the function. So this is the first idea. So using the slope. So again, I don't know what the slope is at 2. It's complicated, but I know what the slope is at 1. So it's so because if y equals ln of x, then oh yeah, that's thanks, Patrick. Okay, you're too fast for us, but it's true that would be a good thing, a good way to do it too. So taking a average of these two things, it would give us something better. But that's not Taylor's approach. So yeah, maybe next time we see that. So dy dx equals to 1 over x. Or rather, I'm going to say that, yeah, use this notation so that way I can f prime of x equals 1 over x. Because then I want to be able to plug in whatever value of x I want. And in particular, f prime of 1 equals 1 over 1 equals 1. So I know that here the slope is 1. So that at 2, probably I get something that's close to, if the slope is 1 and I get 1, so the approximation here should be that 1 unit to the right gives me 1 as a approximation, which is still better than 0. So then I would get that log of is approximately equal to log of 1, right? This. Oops. So that plus the derivative at log of 1. So it's d ln of 1 dx times how far I'm going to the right. So I'm going 1 unit to the right. So from 2 to 1, so 2 minus 1. And this is equal to, so this is equal to 1. And 2 minus 1 is equal to 1. And this is equal to 0. So it's approximately equal to 1. So 1 is a better approximation than 0. So we started with an approximation of 0. So 1 is a better approximation of 0, but it's not perfect because the real value of log 2 is not 1, it's 0.69. So how can we, where did we go wrong there? Why did we overshoot? We started with 0, it was too low. Then we went to an approximation of 1. Yeah, 1, which is too high. So why did we overshoot? Somebody has an idea? Or are you lost? Yes, exactly, Anthony, because the slope is decreasing. So yeah, so let me again show you what we were doing. So okay, so let me share my screen there. Here. So we started as a first approximation. We said, well, log of 1 is 0. So probably log of 2 is 0, 2. So that's 0th order approximation. So this is our best bet for log of 2. But then we said, oh, but by the way, we know that the function is increasing there. So what we can do is start from here and look at what the slope is. We can compute it easily again. And the slope is more or less this way there. So then, and then I know what the distance is. It's a distance of a unit of 1. And what do I reach? I reach a value of 1 there. Oops. But as Anthony said, it's not a perfect approximation because the slope is not constant. This assumes that the slope is constant, but unfortunately the slope starts at 1, but then decreases, 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 so that when I reach 2 here, it's smaller than it used to be. And I would like to have a way of taking this information into account. And this is Taylor's idea. He says, well, I can take into account the fact that the slope is decreasing, but even maybe the rate of decrease of the slope is decreasing as well, or increasing. So I can take the third derivative, fourth derivative, fifth derivative, and an infinite number of derivatives to get to the best estimate possible that will give me something that's as close as possible to 2 there with a polynomial expression. And here is how he does it. Oh, I had a nice picture of okay, so let me show you my nice picture there. So let me go back to the class there. Yeah, I did some work for you. I forget. So this is the 0th order approximation of log 2. It's 0. First order is 1. But then I would like a third order, fourth order, a second order, third order, fourth order, and X order. So this is how we're going to express it. So approximating f of x around x0 with a polynomial expression like this one. So f of x will be, and now that's what's genius about what he shows, is that it's not, if you take an infinite number of orders, then it's no longer an approximation, it's an exact representation of any possible function. So it's g of, let's just write it, g of x, which will be equal to c0 times x minus x0 to the 0, and x minus x0 to the, so this to the 0. So since it's to the 0, it's 1. So this is going to be simply c0, but I'm writing it for just to be exactly formal. C1 times x to the 1 plus C2 to the 2 plus C3 etc. So this is the, if I just take a first approximation of log2, then I just plug in log2 here and I'm done. Zeroth approximation. First approximation is log2, log1 plus, and then C1, you can guess that it has to be the derivative, right? Times x minus x, and x0 is 1. So this is what we had here. Yeah. So this is, this would be C0. This would be C1 times 2 minus 1 is x minus x0. But then what he wants to add is these higher order terms there. And then what we want is expressions for these higher order terms. Oh, it's already almost finished. All right, so I'm not going to have time to finish this, but we can continue it next time. Well, we still have a few minutes. So yeah, so let's still continue a bit. And what he shows is that the trick is that you want as many of the derivative of g to match the derivative of f. So we're at x0. So f of, let's start, g of x0 equals f of x0. And then he wants the first derivative, g prime of x0 equals the first derivative of f prime of fx0. So that's what we have here. We want a function that's at x0, so at 1, its value is the same. So that's what we have here. Its first derivative is the same. It's what we have here. So the first derivative is equal to the first derivative of log, but also the second order derivative is the same. And then the third order derivative is the same. And so on and so forth. For an infinite number of functions. And yeah, so it's I think I can just leave you with these ideas there. And there's the final problem in the TA session that you cannot, it's on Taylor series, but I haven't given you what this expression is. So I'm just going to give it to you next time, so don't worry. And yeah, next time I'm going to finish on Taylor series, give you another example of optimization. And please send me any questions you have about anything in the class that you would like me to go over, and I can go over with everybody. So it's a good preparation for the exam, just sort of a Q&A. And if nobody sends me anything, then it means that I have to show you some other stuff, which I have, so don't worry about it. So yeah. All right, so last some questions before we finish. Yeah, Zine?
Yeah, I'm just a little confused. In this case, what is g of x?
G of x is our artificial function that we want to build to approximate f of x. Right?
Okay. Yeah.
So, and in this example, you see that f of x is the log function. It's the black. And then what we're trying to build is some polynomial expression that's going to look very much like f of x around the point that we know about. And as we said, we know about log 1. We know its first derivative, its second derivative, all the derivatives. It's easy at 1, but at 2, it's hard. So what we're going to use is some very, very good approximation of log 1 around 1, and hope that if we don't go too far, so you see that if 2 is not too far from 1, so the approximation is not too bad. But if I went very, very far, then it would be a bad approximation. But if I'm lucky and 2 is not too far from 1, then the approximation I get at 2 is much, much better. And yeah, since you ask, let me show you what I will get from higher order approximations. So if I take a g of x where not only the first derivative is the same, but also the second and the third derivative, then this is the sort of approximation I'm going to get. So third order approximation is the purple one. Second order, sorry, is the purple one. Then third order is the blue one. Fourth order is the red one. And as you see, so it's always a perfect approximation at 1. But then the more higher order I add, the more I'm able to sort of hug my or spoon with my f of x function, so that when I'm at 2, it's better and better and better approximation. And if I have an infinite number of orders in my approximation, then at 2, it's going to be exactly perfect. So this is what we're going to see next class.
Okay, that makes sense. Thank you.
All right. So anyway, so Taylor is a more advanced topic. So it makes total sense that you don't get it perfectly right away. So we're going to continue here next time. All right. So thank you very much.
Thank you.